We are in 2.3 looking at prime numbers. Before we do that, I have a couple of things to look at with you. Do you have any questions before we leave Wiley Plus? Anybody have homework questions? We have 2 tutors for this class, and they're willing to set up study groups, but they need to know when people would be interested in attending. So if you went to a study group, your tutor would each week go over what you can expect on the quiz and make sure you feel comfortable doing the work that will be handed in on the quiz. So they'll ask you to do some of the different work and then check it and make sure you're getting it right. So some of the things that we do take practice, and if you can go to a study group, that would be wonderful. If you're interested in a study group, then put a tally mark in the times that you can meet. So I crossed out Friday, Tuesday, and Thursday, and there's just really open Monday and Wednesday afternoons for a study group. But if any of those times work for you, put a tally mark there. You can put a tally mark in more than one spot, okay? And hopefully we'll have a couple of study groups. Can you please pass this around? The life lesson in this section is that simple observations often have deep consequences. We see that in the proof that we're looking at with the proof that there is no greatest prime. So let's go ahead and take a look at that further today. So the strategy was for us to find a number, find a prime number larger than a given number. So some number that we work with. Find a prime number larger than whatever that particular number is. Which had a remainder, by finding a number, sorry about that, by finding a number with a remainder of 1, when divided by a number smaller than or equal to whatever number we put in that box, okay? So we worked at finding a prime number larger than a particular number. We did 3 and 4 and 5. By finding a number with the remainder of 1 when divided by a number smaller than or equal to that number. So suppose that number was 6. Do you remember how we found, how we started in the process to find a number? So first we found a number that had a remainder of 1. Yes?
So didn't we just multiply 5 times 4 times 3 times 2?
Yep.
And then add 1 at the
Good.
end?
So we would multiply 2 times 3 times 4 times 5 times 6 and add 1, and that gives us a number that when you divide by 2, 3, 4, 5, or 6 has a remainder of 1. And we can check that out. So let's go ahead and multiply this out. 2 times 3 times 4 times 5 times 6, and then add 1 on.
721.
Thank you, 721. So if you take 721 and divide it by any of these numbers, you get a remainder of 1. the way you can do that, we're gonna need to know how to find remainders in the next section too. So if you weren't quite clear on how you find the remainder, take your calculator and divide it by the number you're dividing by, say 2, and you see how you get 360.5? Take the whole number, the 360, take the whole number, the 360, and multiply that times the 2, and you get 720. And then when you subtract, you get a 1, and that's the remainder. So when we're looking for remainders, we take the number we're dividing, say 721, let's do by 6 this time. And we get 120.16 repeating. So we take the 120, the whole part, and we put that right here. And then the 120 times 6, that's 720. And when you subtract, you get a 1. So that's the remainder, 1. So you can use your calculator. You don't have to do this all long division, but you're looking for that whole number in the division to multiply by the 6 and subtract like you do with long division. So you can try that with 2, 3, 4, and 5 as well. 3, 4, and 5 as well, and you'll see that each of those will have a remainder of 1 when you divide them into the 721. Is 721 prime? Sometimes that number does come out to be prime. Did anybody decide if 721 is prime? Okay, because we're looking for a prime number larger than 6, and 721 is definitely larger than 6, but is it prime? Let's see if it is. It's not even, so I'm not going to try dividing by any evens, and it's not divisible by 3, so I'm not going to.
It's not prime. It divides out by 7, and you get 103.
Thank you. And 103 is prime. Okay, so this process then gave us a 721, which was not prime, but the prime factorization of 721 has to have numbers that are prime that are larger than 6. It couldn't be 6 or 5 or 4 or 3 or 2 in the prime factorization because those numbers did not divide evenly into the 721. So we've found that 721 is not prime, but its prime factorization has numbers that are larger than 6, prime numbers larger than 6, because 2, 3, 4, 5, and 6 themselves will not divide evenly into the 721. So that's the brilliance of this proof that we're going to look at. Euclid gave us this proof more than 2,000 years ago that we're going to be looking at. And the beautiful and elegant part is constructing this. Now, proof has to be true for all situations. The proof has to be true for all numbers, not just for 2, 3, 4, 5, or 6. So instead of using the number 6 right here, we're gonna use the number m. So we're gonna find a prime larger than any number, m. So m could be 2,379,000. It could be 20,782,000. So there is no largest number, and m is any number, so it could be as big as it needs to be. So let's actually get to the proof. This was the strategy. Oops. So this up here I labeled strategy, okay? Oh, I did that already. So double labeled strategy. And now we actually get to the proof. And this is the proof that I'll expect to see on your quiz. So on your quiz 1, I'll say, prove there is no largest prime, and this will be the proof that I expect to see. So we're going to prove that there are infinitely many primes. Or equivalently, that there is no largest prime. Prove that there are infinitely many primes, or that there is no largest prime. Same thing. Okay. Let m be any natural number. Let m be any natural number. We need a prime larger than m. Let m be any natural number. We need a prime larger than m. Let b equal, b stands for big, so b is our big number. B equals 2 times 3 times 4 times ... times m plus 1. Okay, now b is bigger than m. And b is bigger than m. So b is a big number, it's bigger than m. B is either prime or not prime. B is either prime or not prime. There's not any more choices than that. Prime or not prime. If b is prime, we are done. If b is prime, we are done. We found a prime bigger than m. Okay. If b is not prime, it has a prime factorization. If b is not prime, it has a prime factorization. Let p be a prime factor of b. Let p be a prime factor of b. So p is one of the prime factors of b. P is not 2, 3, 4, comma, ... comma, m, because they don't divide evenly. They don't divide evenly into b. P is not 2, 3, 4, comma, ... comma, m, because they don't divide evenly into b. So P is a prime larger than m. So this is a proof that's true for all numbers. We found a prime number larger than m. Now we talked about a proof being an irrefutable sequence of statements that lead to a conclusion that is inescapable. Okay. So let's see if we can look at this proof and see why it proves what we need it to. So the proof has to be true for all numbers, otherwise it's not much good. Okay, and so M stands for any natural number. We did this with M6 in a specific example up here. Okay, but now M stands for any number. And the goal is to find that there's a prime larger than M. That's going to show that there's infinitely many primes, that you can just keep going and find a bigger and bigger prime. So this is the heart of the proof. The B is the 2 times 3 times 4 times ... times M plus 1. However, putting this on your quiz will only result in like 1 point out of the proof. Proofs and things that you have to practice, let's put practice next to this. Proofs and things that you have to practice are worth more points on quizzes than things like multiple choice or yes, no, true, false. Okay. So this does take practice, and it will be worth more points because of that. Okay, so we make this number B. Why do we care that B is bigger than M? Why does it matter that B is bigger than M? Maybe I should ask, why is B bigger than M? How do you know B is bigger than M?
It's the product of M times everything.
Yeah, because at least it's 1 bigger, right? Yeah, okay. Okay, and why does it matter that B is bigger than M? So if you hand in your proof without this statement, you're going to lose a point because it's necessary. Why is it necessary that B be bigger than M? Yes.
B is either a prime or not a prime, and it's bigger than N because it's equal to, because if it doesn't have a prime, then it's not a factorization, and P is one of the prime factors of B.
Good. Okay, so you're picking out parts of the proof coming up, and they rely on the proof itself that you're trying to find a prime larger than M, and so you need to start with numbers that are bigger than M. Okay, and like you said, then if B is prime, then you're done because you found a prime number that's bigger than M. Okay, so that's why B has to be bigger than M, because then if B is prime, then you're done. You found the prime bigger than M. So if B is not prime, then it has a prime factorization, and that's a theorem that we looked at and we wrote down in our notes, that either every natural number is either prime or it has a prime factorization. But the big thing here is that P is one of the prime factors of B, and that P has to be bigger than M, because all the numbers from 2 up till M divide evenly into that. I'm sorry, none of the numbers from 2 up to M divide evenly into B. So P can't be one of these numbers, because prime factors divide evenly into your big number B. Anybody have any questions on that proof? Then this is one of the things that you should practice each week, okay? And if you go to study group, they would help you with practicing there. If you want to just try practicing on your own and then checking it, just make sure you have all these statements and didn't lose any. And sometimes students write this on their 3x5 card, but a 3x5 card only holds so much, right? So number theory has been one of the earliest mathematicians' interests because we've had numbers the longest, along with geometry. And so we have lots of interesting stories in number theory. We'll look at the mostly true story of Fermat's last theorem in your textbook. This is actually quite a bit true. The only parts that are, when he says mostly, is he kind of dramatizes it a bit. It was a dark and stormy night. Rain pelted the wavy window pane. Wind seeped in through cracks in the window frame. A candle flickered uncertainly in the cold breeze. It was 1637. Pierre de Fermat sat in the great chair of his library, poring over the leather-bound Latin translation of the ancient tome of Diophantus Arithmetica. He concentrated intensely on the ideas that Diophantus had written 2,000 years before. During those 2 millennia, whole civilizations had risen and fallen, but the study of numbers bridged Fermat and Diophantus, spanning centuries and even transcending death itself. As the night wore on, inchoate ideas, at first jumbled and ill-defined, began to weave a pattern in Fermat's mind. He gasped as insight and understanding began to weave a pattern, to take shape. He was seeing how the parts fit together, how the numbers played on one another. Finally, it was clear to him. On that fateful night in 1637, he wrote in the margin of Diophantus Arithmetica the statement that would make him famous forever. He wrote, "It is impossible to write a cube as the sum of 2 cubes, or a 4th power as the sum of 2 4th powers, and in general, any power beyond the 2nd as a sum of 2 similar powers. For this I have discovered a truly wondrous proof, but the margin is too small to contain it." How many of you have heard of Fermat before I read this to you? Anybody heard of Fermat before? Well, Fermat's last theorem was a big, outstanding theorem for over 300 years. It wasn't solved until my lifetime, after I was in high school. I remember talking about it with my high school teacher, and him saying there was a $1 million prize available if you could solve Fermat's last theorem. Fermat had a number of theorems, and he just was notorious for not writing out the proofs. He would think of them, and he would tell his mathematician friends about them, but then he would not write out the proofs. So all of his other theorems have been solved within, at least by the 1800s. But this one was called Fermat's last theorem because it was not solved. So we're going to take a few minutes to look at this, Fermat's last theorem. So you remember this one? What theorem is this one?
This is the Pythagorean theorem.
Good, the Pythagorean theorem. So that's been around since before, like around 400 BC. A squared plus b squared is c squared. So we use that in right triangles, right? So what Fermat is saying, it is impossible for a cubed plus b cubed to equal c cubed, or a to the 4th plus b to the 4th to equal c to the 4th, or a to the 5th plus b to the 5th to equal c to the 5th. That there are no natural numbers that you can make these with. The Pythagorean theorem with those exponents of 2 are it. That's as good as it gets. It's impossible. It's not only that it doesn't happen sometimes, it's actually impossible for a cubed plus b cubed to equal c cubed, and so on. Now, like here for an example, a squared plus b squared is c squared. Just take the numbers 3, 4, 5. You get 9 plus 16 equals 25. So 3 squared plus 4 squared equals 5 squared. You get 9 plus 16 is 25, which is true. And there's lots of what we call Pythagorean triples, natural numbers that make that true. But it's impossible for this. Now, because he did this all in his head, there should be a beautiful, elegant proof, not too long, like the proof that we did for there is no largest prime. There should be a beautiful, elegant, simple proof like that. But no one has yet found that beautiful, elegant proof. What Wiley did find was a terrific proof that took decades of his life to come up with, and over 10 hours for him to prove it. So this is the man who actually proved it, Andrew Wiles. I said Wiley, and it's Andrew Wiles, in 1994. And just presenting it for the first time took 2 days, 10 hours of presentation. And then the mathematicians at his presentation, it took many days afterwards examining his proof closely and making sure it was indeed a proof. And his proof led to a number of different mathematical areas and proved a number of important and difficult theorems, including some new theorems from geometry. So it's amazing proof, but there's probably a beautiful, elegant proof out there. If you're a person who's into number theory, you might be able to find that. So this one is proven. Fermat's last theorem, proven. It's impossible for these a cubed plus b cubed equals c cubed, a to the fourth plus b to the fourth equals c to the fourth, and so on. Now I'll be writing the 3 different theorems on your quiz. This is one of them, and I'll just take the quote from the book, and I'll put Fermat's last theorem there. Okay, and that one's been proven. But I'll also take these other 2 proofs, these other 2 theorems, and put them, these other 2 hypotheses, and put them in your quiz as well and ask you about them. So these are all in the end of section 2.3. This one is the twin prime question. So the question here, are there infinitely many pairs of prime numbers that differ by one another by 2? Okay, so prime numbers that differ by one another by 2 are twin primes. So there's 11 and 13, for example, 29 and 31, 41 and 43. We can get some in the larger numbers too. 101 and 103 are twin primes. So twin primes differ by 2. Let's see if I brought that list with of primes, the first 100 primes, and we could look at that. Well, I left that in my office. Does anyone want to guess whether that's been proven or not? It's called a question right here. Has it been proven or not proven? Sometimes proving something's impossible is just as good as proving that it is possible. So the question is, are there infinitely many pairs of prime numbers that differ from one another by 2? That's an open question. So some number theorists will be working on that to determine, is it possible that there's an infinite number of twin primes, or is it impossible that there's an infinite number of twin primes? So that's an open question. Here's another question. Can every positive even number greater than 2 be written as the sum of 2 primes? Okay, so let's just pick a number, see if we can write it as the sum of 2 primes. So here's a number, 16. Whoops, here I write it so it's on screen. 16. What are 2 primes that you could write that add to 16? And there's not just one way to do these. Good, 11 and 5. Okay. That's another example. How about 32? What are 2 primes that add to be 32?
29 and 3.
Good, 29 and 3. So that's an open question as well. Can every positive even number greater than 2 be written as the sum of 2 primes? That's also your class activity for today. You're supposed to put an example. You could come up with your own example, or you could use one of these. You don't have to take a photo. You can just type the numbers in if you want for your class activity, whichever is easiest, okay? So that's your class activity, to give an example of the twin prime of the Goldbach question. So on the quiz, I'll ask which of those three questions are proven, if any. Okay, Fermat's last theorem, the Goldbach question, or the twin primes question. And I'll ask for examples of the Goldbach question and an example of the twin prime question. And those will be written on the quiz, so it's not like you have to write them on your 3x5 card, okay? Unless you want to remember, you do need to remember which one of those three is proven. Which one of the three is proven? Twin prime, Goldbach, or Fermat? Yeah, Fermat's. Fermat's last theorem is proven. Okay. So mathematicians do a lot of research. Not me. That's why I'm a lecturer instead of a professor. I got my master's degree in math, but I did not care to do research, and so I just learned a lot about a lot of different. I took 41 credits in all different areas of math. I didn't want to research and focus in just one because I wanted to teach. But people who are professors have to do research, and they must enjoy it, or else they wouldn't pursue that field. Okay. But the point of math research is very interesting to me. For example, you might think of those theorems that we looked at in those open questions and not be interested and wonder why anybody would care. Any mathematical method used at school or work or anywhere was figured out at some point by a mathematician. Another mathematician may have proven that it always works, and another may have worked out how to use the method in the real world. So that's how the research works for mathematics. This article talks in particular about primes, so that's why I included this article. Here is an example of such a recent result. It deals with the distribution of prime numbers, like 7, 11, 23, or 37, which you cannot divide by another natural number other than 1 or themselves. We found prime numbers as large as 22 million digits long, and researchers are still looking. As it turns out, prime numbers slowly but steadily appear less frequently. They thin out among the larger numbers. A breakthrough in 2014 showed that no matter how high we go among the numbers, we will always find two primes that are closer to each other than some constant number. That number was initially a whopping 70 million. So they're saying that the primes will always be within 70 million numbers of each other. Well, that's really big. Other mathematicians then set out to reduce that 70 million, and now the best that the author is currently aware of was a much more manageable 246. So mathematicians do research just because they're interested in an area, just because they're interested in number theory or geometry or what have you. And then eventually it leads to real life applications. My math teacher used to say that mathematics would be 100 years ahead of the sciences that would use it. Let's go ahead and take a look at the next section. I'm going to go on to an application of numbers in 2.4. And we start with a question. I'll fill this in. Today is Monday. September 16th. Just double check that. Yep. What day of the week will Christmas fall this year? So don't look on your computer, okay? Don't look on your phone. I'd like you to think through how you might figure out what day of the week will Christmas fall on this year? I thought about using Thanksgiving, but you know that just didn't work here. Okay. So what day of the week will Christmas fall on this year? So think of a strategy of how you might do that. How you might figure that out without looking at your phone. Yes. Oh, are you raising your hand? No. Okay. So without looking at your phone, what would be a strategy? Yes.
Well, you could do like 25 minus 7 since it's Christmas is on the 25th of every year.
Okay.
You could do minus 7 December 18.
Oh, okay. So backtrack. Just keep subtracting 7 days, 7 days. That would be one strategy. Yep. You'll need to know how many days are in each month for that, right? Did anybody learn a way to do that? Figure out how many days are in each month? I learned a poem when I was in school. If you learn nothing else today, you learn a poem to tell how many days are in each month. "30 days has September, April, June, and November. All the rest have 31 except for February." Okay, so you're going to need that. Did anybody think of a different way to go about this? Okay, then I'll have you work on this in groups, okay? So groups of 3 or 4 people, I'd like you to talk about this and see if you can figure out how to figure out what day of the week Christmas falls on this year without looking in your phone or your online.
Every month you just figure out what you do for
A couple of groups have found the method that I was planning to work on with you in the class for this. They figured out how many days are left till December 25th. So this is 2.4. Your author calls it clock arithmetic. It's modular arithmetic. Modular arithmetic. So your classmates and maybe your group too figured to find how many days there were left until December 25th. So in September, let's see, September, October, November, December. Anybody else keep a Christmas fund? You save money, save money up for Christmas presents. I do that. It comes every year, you know, and you're going to want to spend money then. Okay, at least I do. September. Today's the 16th, so there's 14 days left in September. October has 31. November has 30. And the 25th is what we're looking for in December. add these up. We have 100 days. Okay, so then what did you do after you found out how many days were left? What did you do in the back there, Hayden? I think that was you who told me. Was that you?
No.
Oh, okay. All right, what did you do?
I didn't do this way.
Oh, okay. Who did it this way that told me? Nobody?
Divide by 7.
Okay, divide by 7 because you're taking out weeks here. So 100 divided by 7 is 14 point something. So you take the 14 here, and that means you can take away 14 weeks. 14 times 7 is 98. So if it was just 14 weeks from now, it would, December 25th would fall on a Monday, because today's Monday. But we're going to look for Wednesday then, because we have 2 more days after you take away 14 weeks. So Christmas will fall on a Wednesday this year. Well, when we take away multiples of 7 like that, that's called modular arithmetic. It's also what your author calls clock arithmetic, and so we're going to look at a clock and get some practice with modular arithmetic by looking at a clock. Okay, so suppose it is 10 o'clock. What time will it be in What time will it be in 38 hours? So it's 10 o'clock, and the question is, what time will it be in 38 hours? Are you adding it up? So the hour hand's going to go around the clock and come back to the 10 once, and that will be 12 hours. And it'll go again, and it'll be 24 hours. It'll go again, it'll be 36 hours. And then there's 2 more hours.
It'll be 12?
Mm-hmm. 12 o'clock. So in 38 hours, if it's 10 o'clock in 38 hours, it'll be 12 o'clock. So we're taking away multiples of 10. It's not like when you're working with the natural numbers and you just, you go up to, your clock doesn't go up to 58 or 68 or whatever. It goes only up to 12. So what time will it be in 22 hours?
From the 10 o'clock or
Yep,
the 12?
from the 10 o'clock.
It'll be 8 o'clock.
Let's see.
It's like it doesn't go around the...
Good. So it goes around 12 hours, and then it needs 10 more hours after that. So from 10 o'clock, 10 more hours would bring you to 8 o'clock. So that time you just took away 12 hours from the 22 hours, and there's still 10 more hours to take away. how about from 10 o'clock in 412 hours? So there's where you might use your calculator, and that division that I was talking about, where you take 412 and you want to know how many times 12 goes into there, so you can take away those multiples of 12 hours, because every 12 hours you're back to 10. Every 12 hours you're back to having the 10 o'clock. So let's see if we take 412 and divide by 12. We get 34.3. So there's 34 multiples of 12 here that I can subtract away. Just take 34 times 12 and get 408. So when I subtract away multiples of 12, I subtract away 34 multiples of 12, leaving 4. So I'm going to take the hand that's spinning around, 408 hours worth, 34 twirls around, discard those, and then go just 4 hours from there. 1, 2, 3, 4. 2 o'clock.
Thank you.
Okay, so I'd like to make sure that you're getting the hang of this. So from 10 o'clock, what time would it be in 515 hours? So I'm going to walk around and see how you're doing and making sure you get the hang of this, okay? Raise your hand if you're stuck.
I'm understanding like going around the clock. It's just like the division that I'm not like understanding.
So what would you put in your calculator?
And it has to be like 515 divided by something, obviously. But I guess I'm more confused on whether or not to use like 12 or 24. That's where I'm like stuck.
Use the clock.
Yeah.
That's how much the clock is.
Okay. Yeah.
Is that okay?
Yeah, I understand what you're saying. It's like there are like 12 numbers on the clock, so you use that instead of like the 24 hours in a day.
Exactly.
Okay, thank you.
Anybody else want to have me come by and look at their work? So ignore the 24 hours in the day and just look at the clock, because there's 12 hours on the clock. So every 12 hours you're going to be back to 10. You should have taken the 515 and divided by 12 to see how many of those 12s you can take away. You get 42.9 something. So that means you can take away 42 multiples of 12. So 42 times 12, that's 504. And that's what you're subtracting then. So the 11 is what we're interested in. You take away 42 multiples of 12, because your hand keeps going around the clock, and we don't care. Every 12 hours you're back to 10. But after you go around 42 times, then there's only 11 hours left. So you'd come out at 9 o'clock. Anybody else get 9 o'clock? Okay, good. Well, that's modular arithmetic, and it's used in a number of different areas. We're going to look at those later on Wednesday. So we'll stop here and pick it up on Wednesday, okay? I'll see you then. Don't forget to submit your class activity for the gold box question. On Canvas?
No, I committed to goal docking already.
Okay.
On the like module talk one.
I don't remember. I think it's one we didn't get to yet. Yeah, we didn't get to it. Now I'm thinking about it. It's an application that we'll get to Monday.
All my Wiley classes.
For the whole year? For what?
All my
Oh, good for you. Good for you.
Wow, look at you flexing on all of us. Wow.
I don't mean to. I just stuff that you haven't even gone over. It's not that hard really, and I got pretty good score on those. The 14.4 not so good the score, but I did okay.
Okay.
I did okay on it. I think I got about 5 of the questions out of 9, 5.83 out of 9.
When you don't know the lesson yet, that's very good.
I didn't know that stuff. I used a lot of info, so like, I used a lot. It was just going back to the textbook. I know, same. Yeah.
The 2.1 and 2.2 assignments were a lot easier for me than the chapter 1.
Oh, yeah, chapter 1, there's just not a set way to do it, and so it takes a lot of, every single problem's different and puzzling.
Yeah,
I'm glad
I did a lot better in the 2.1 and 2.2 than the chapter 1 and stuff.
Good. You should find that for the rest of the semester.
Yeah.